We have a string S and an array of strings for word dict, representing a dictionary. We want to add spaces to S to break it up into a sequence of valid words from word dict. We are required to return an array of all possible sequences of words, aka sentences, and the order in which the sentences are listed is not significant. Now, the same dictionary word may be reused multiple times in the segmentation. And this is an example. So we have this word, S, and this dictionary. And we want to break it down into all the possible words we can form based on the words in the dictionary, all the possible sentences we can form by adding spaces to S uh, based on the word, the lexicon here. So we have cats and dog by putting it between S and A and between D and the two Ds, and cat, sand, dog, right, by moving the space around. So I hope that's clear. And we have this example, and this one returns nothing because there's no way we can put the space. So whatever sentence we're returning has to be built with exclusively with words from the dictionary. And because they skipped a D here, right, there is no way for us to do that. So we return an empty string. And now there's a part one of this problem from a few days back, and the solution in the code is gonna build on that, right, on the solution that we came up with there. And so what does that look like? I'd like to look at the old solution. So before, the version 1 of this problem asks you to check if it's even possible, right, to add the space and create sentences with the words here by adding spaces. Check just to check if it's possible. Now this version is asking us to give every possible sentence combination that you can get, right, beyond just finding out if it's possible. However, it builds on the same process. So it's kind of a two-pointer dynamic programming problem, right? Two-pointer pattern and a dynamic programming pattern type of problem. And you basically have two cursors, and you are building up in the spirit of dynamic programming and divide and conquer algorithms. You are building up a solution by, for instance, between this word, assuming we only had each letter of this word piece by piece, and then assuming we had only V, the answer to our question helps us find it, things assuming we have just VE, helps us find if assuming we have just VEG, and so on until we get to the full string, right? And so if you watch that video, it's like 8 minutes long, right? We are moving, checking the prefix, right, that we get by moving I. I is what helps us track things, move from character to character. But J helps us not just consider the forward pass, but within each subproblem, right, the suffix as well, like if there is something there just to be exhaustive. And so that helps us quite a bit, actually. So for instance, we keep moving here, and I think we can look at the old solution. So this is the prior solution, right? And we can learn a lot about this problem by looking at the past solution for version 1 of the problem and version 2 over here. So we see that a lot of things are similar, right? We get the length of the string, we create a set so that we can look things up in all one time, and then we have our DP array. In this case, we're filling it with false, but in this case, we're filling it with one empty array. Okay. So this is the current solution. So the first element we set to an empty string in this case. The first element we set to true in this case. And that's because if we have nothing, right? If we have no character in this string, right, then our response is going to be an empty string, basically. That's the most we can do. And so how do we set up this iteration with I and J? Very simple. You loop from I, from 1 to the end of the string length, and then for J up until I, right? That's how we do that. And you notice that it's the same thing happens here. I up until the length of the string, J up until I. And now you will notice we were going to come to this temp and suffix in a bit, but if you look at the code just at a glance, you see that there's not much difference. right? Between this version and this version. So understanding this version, you can say is like a key to understanding this version. So in this case, we're checking if the substring from J to I is present in the word set, and if dp of J is true. In this case, we have the suffix from J to I, right? I separated it out here. And then we're checking if it's inside the word set. And if it's inside, we're gonna get the valid sentences from previously computed subproblems and append that suffix to it, depending on whether there was something there in the first place. So the substring in here, right? Add it if there's something in there, right? If it wasn't an empty string, then put a space so that we can add the suffix. Otherwise, don't put a space, right? Just add a suffix. And so diagrammatically, right, while in this case, we were moving I and J to set, we're looking for a Boolean value. In this case, we're looking for strings. And so if you pay attention here, they didn't draw the I and J, but it's still there, and it's worth just visualizing that. So we set temp as we showed in the code earlier. Set temp to an empty string, because we're going to use temp to construct our subproblems. So assuming we had just V in this vegan, right? Assuming there was only V here, right? The solution to that, because V is not in the dictionary, right? We don't do anything with temp. So because this isn't true, right? Temp stays the way it is, like a negative thing, an empty array, and that's why it looks like that. Okay. And then next we go VE, right? So, and I like that it's even similar here. So we went from V, right, to looking at V and E over here. And V and E doesn't appear in our dictionary in this case. And so temp stays the way it is. But then we don't just check V and E, right? We also check E, right? So not just V, but also E. And E isn't in the dictionary, as you can see here. So that's how we check E. It's not in the dictionary. So temp stays the same all across this particular iteration window size of 2, right, from here to here. Okay. It stays the same, negative array. And then here we have VEG. Oh, there's actually VEG here. Oh, and look at that. In this case, there's VEG as well. So that's how we end up. That's how we end up. That's how we end up reaching VEG, and that's how we end up reaching VEG. And then in this case, right, we do have something, right, prior, which is the empty string. So in code terms, we get the suffix, which is VEG, and in this case, there is something in the dictionary. And so we're going to loop through everything for where J is. And in this case, if VEG J is out here in the beginning with over here with the empty string that we initialized to 0. And so we append VEG to everything inside there, which is just an empty string in this case. So that's why we get VEG here. And then that's what it's going to be set to. But before we finalize that, I believe it's before we finalize that. Yes, we're building up temp, and that's for this particular IJ combination. So we're going to increment J. J is going to move forward. Although J technically doesn't have to move forward, right? Since we found something. But to be thorough, I mean, we can remove it EG just to see if there's something smaller in there. Just in case, because if VE was in here, then that would be useful, right? If V was actually in the dictionary and EG was in the dictionary, then now it would be useful to check that. So it's worth exploring in this case. And so we keep going. So we have something inside DP, right? We finally set it out here. Like once we're done looping through J, right? Set it. up here, whatever temp was, and we we move I and keep doing the thing up until we get to the end. We build till I has reached here. So we use all the sub problems to find the final solution here. And that's that about that. Right. So the key is when J is over here, right? We look up dp of J, all the solutions for VEG, for instance, and add add and to all of them. So we're gonna add and here to that because it's possible to build it from here, and then we're done. So admittedly, this is probably not my best explanation video, but I hope like in your time you can look at both solutions and draw the connections, so that you can see how they're related, and you just at the end of the day return dp of n just like last time. Bring the last one over here just like last time, and that represents the full thing, all the sentences we've been building up. So very similar problems. I feel like you want to know this first before you know this one, and code is in the description, as well as a case for you can build with the debugger. Although admittedly the debugger didn't do me as much good understanding this problem as just looking at these diagrams, right, between the two and spotting the differences between solving them. So yeah, I'd say that's it for this problem. Let's look at the time complexity. Very complex time complexity, which is, I mean, to be expected, dynamic programming problems of this kind. So what we have n squared somewhere here, right, where n is the length of the string itself, and then w is, what is w? Okay, they have this very lengthy explanation, but I'm more interested in w. What is w? Or I think I got it. W is the length of the dictionary, I think. So OLW time to search through it. Is the explanation of this wonky time complexity. N is the length of this string S. W is the, I believe, the length of the dictionary. And I think that, well, in our case, we use a set, right, for our solution. They didn't in their case. But still, the time it takes to build the set is probably the same. So, of W. And then they go into some more detail here that, quite frankly, I don't have a feel for. But the space complexity is O of 2 to the n. And yeah, very mathy, a very mathy problem. And again, we're not mathematicians, right? We're software engineers. So don't sweat it too much. You can internalize this if you know maybe the company you are interviewing with asks this question a lot, but otherwise, just know how the problem is solved and carry on with your life. Cheers.